Yeah, good morning, students. So, welcome to the second week, first class. Today, that is 10th of August 2020, and we have the class at 9 a.m. to 10 a.m. So, just before starting the class, I would like to make it very clear to you that assignment number 2 for week 2 is posted in the course web. The directions given from the head of the department and our beloved principal. So I have modified the assignment, and it was slightly modified. It will be similar to your first assignment. See, I'm just displaying the assignment on the screen. If at all it is visible, somebody respond. It is visible to you? Is this assignment visible to you?
Yes, sir.
Yeah, okay. See.
Yes, sir.
Yeah, okay. For the first 5 minutes, just I'll go through the assignment, and next 5 minutes I'll be explaining you whatever we have dealt in the last class. Then I'll go with today's session, right? So assignment number 2, the topics which I have covered in assignment number 2 is stress strain diagram, elastic limit, Hooke's law, and elastic moduli, right? There are two different elastic moduli which we will be discussing today again, and so it is common for both CE1 and CE2. So I have posted it yesterday, that is 9th of August, that is Sunday, and you have to submit it on 16th, Sunday again, and I'll be correcting and posting the marks the next week, that is 23rd of August. So whatever the assignments you have written, right? So there are some clear-cut instructions which are given at the last, right? So these are the directions given by our beloved principal, sir. So you have to follow these instructions. Okay. So I don't know how many of you are maintaining a separate notebook. Maintain 2 notebooks for this course, right? One notebook for class notes, the other notebook for assignments. So guidelines for assignment submission are also clearly given here. You have to write assignments in assignment notes only. Okay, you should not mix up all the assignments. Try to maintain a separate notebook for assignment. You are not write the questions followed. You are okay by the answer. Okay, on every solution page you should write your roll number and name to appear at the bottom of every page, right? Either you can also write it over the top. Assignment number 2 appear at the top of every page. Assignment number 2, for example, you are writing assignment number 2, right? This is assignment number 2. You have to write it as assignment number 2, week 2, exactly at the top of the page, and at the bottom of the page your roll number and name should appear. Okay, that means you have to draw the border. In the first year itself, I told you, you have to maintain a very neat notebook, right? Notes, because engineering mechanics and strength of metal, these are the core subjects. They will be useful for you for GRE, TOEFL, IELTS, and every things, right? Not GRE, TOEFL, but GATE and some other examination. Okay, scan the solution page, group as PDF document. Okay, you know very well about how to scan the document. Save the PDF document with your roll number, right? Don't save it as document number 1, document number 2, or your phone number, your nickname, right? Like that. Me roll number ke edit here, right? Your roll number underscore assignment number dot PDF, right? It should be your roll number. For example, your roll number is B16 CE001, right? And that should be underscore of assignment. Assignment number. How much is what exactly is assignment number 1? It is 2, right? 02. And you have to send that file. For example, it is given here B18CE 000 underscore A1 PDF, right? Now upload the solution file to Google Drive link. So I'll be posting the Google Drive link to you in the group, right? So you have to just upload that file to that particular Google Drive link. Okay. And whatever the assignment you have written, you have to submit the assignment notes whenever you start attending the classes physically. Is that okay for you? Is it clear to you? Respond, somebody.
Yes, sir.
Yes, Tarun Bandari, you should be active in the class.
Yes.
Is he here? Are
Yes,
you here? Right, very good. Right, okay. What do you see on the screen?
Class 1 week.
Yeah, week 2, class 1. That is today at 9 a.m. to 10 a.m. Okay, see, the main objective of today's session is, after completion of this class, you should be able to learn the concepts of Hooke's law, modulus of elasticity, rigidity modulus, Poisson's ratio, stress strain diagram, and its key features. And also, we are going to solve some problems which are related to stresses and strains. Right. So in the last class itself, I gave you a very little introduction about what exactly is this Hooke's law, what is elastic modulus, modulus of elasticity, Young's modulus, and everything, isn't it? So this Hooke's law, it is not a new thing to you. You might have learned about Hooke's law in your lower classes, 9th or 10th standard, as well as you have studied or you have learned about Hooke's law in your BTech first year, first semester, that is engineering mechanics, and also in physics, right? So can somebody recapitulate what exactly is this Hooke's law? Respond. See, I told you my class will be like an interactive session, right? So unless you respond, right? Otherwise, I will call you by roll numbers. 63. Who is 63? 63.
Yeah.
Yeah, what is Hooke's law?
Yeah.
Respond.
Stress is directly proportional to strain within the elastic limit.
Stress is directly proportional to strain within elastic limit. Next, rule number 112. 112. Rule number 112. Okay, I'm noting down the roll number here. Roll number 112 is not responding. Next, 65. Who is 65?
Within the elastic limit, the stress is proportional to strain produced by the stressor.
Next, rule number 117. Absent today.
There is no number, sir.
Those who are not responding, I'll note down your names and roll numbers. Yes, roll number 117.
117 is not there.
You don't have 117. Next, 120. Okay, right. So it's very simple, right? It states that when a material is loaded within elastic limits, the stress is directly proportional to strain, right? Now, stress is directly proportional to strain. The ratio of stress to strain is always constant, right? When stress is directly proportional to strain, the ratio of stress to corresponding strain. Suppose I took a tensile stress to the corresponding tensile strain, right? Or compressive stress to the corresponding strain is a constant within the elastic limits. Now, what do you call that constant as? What do you call that constant as? It is called as modulus of elasticity or Young's modulus. That's very good, right? Okay. So modulus of elasticity. Now modulus of elasticity is represented as capital E. The other name of modulus of elasticity. Can you tell me what exactly is the other name of modulus of elasticity? What do you call it as?
Yes.
Young's modulus.
Yes, very
Young's
good. Very good. It is called as Young's modulus. Very good. Right. So modulus of elasticity, or it is also called as Young's modulus, the ratio of tensile stress or compressive stress to the corresponding strain is called as modulus of elasticity. Okay, so it is called as modulus of elasticity. Okay, so on the screen you can see tensile stress by tensile strain, or compressive stress by compressive strain, or it can also be represented as capital E, which is equal to sigma divided by E. Okay, sigma divided by E. Right. So whenever you see some formulae or some equations, I told you earlier that you have to maintain a separate notebook. I'll be sharing some information to you. You have to make a note of that one. Okay. I don't know how many of you are making a note of these things. Capital E is equal to sigma divided by E. Sigma is stress. Which type of stress it is? Either it may be tensile stress or compressive stress. By small e. Okay. Sigma divided by E. Tensile strain or compressive strain. Next, see, here I gave you values of different material, values of E, right? Young's modulus. Now for steel, the Young's modulus of steel will be 200 gigapascal GPa. It will be varying from 200 to 220. For wrought iron, it will be 190 to 200. For cast iron, it will be around 100 to 160. For copper, it will be 90 to 110. For brass, it will be 80 to 90. Aluminum, it will be 60 to 80. And timber, it will be 10. Right? So the same thing was also asked in assignment number 2. Right? So I'm not going to share this data to you. Right? It was asked in your examination. It will be asked in your examination. And also it will be asked in your assignment. So for this thing, what you need to do is whenever you see such type of information on the screen, you have to make a note of that one. Okay. So for steel, it will be 200 to 220. Wrought iron, it will be 190 to 200. Cast iron, 100 to 160. Copper, it will be 90 to 110. Brass, it will be 80 to 90. Aluminium, 60 to 80. Timber, 10. Now, a question to you. What will be the modulus of elasticity for rubber and plastic? Right? I did not give plastic here. You have to determine, you have to find out. And additional question in the assignment, you have to write down the modulus of elasticity for plastic as well as rubber. Right? Is that okay? Right. Next, the units for these things, whatever the value which I gave here is GPa, gigapascal, right? Or giganewton per meter square or kilonewton per millimeter square. The Newton per millimeter square can be represented as megapascal, right? Megapascal. So that is multiplied by 10 to the power 3. Again, it will be called as kilonewton per mm square, or it can also be called as giganewton per meter square, or we can also call that one as gigapascal. Okay? Right. Next one, modulus of rigidity. We can also call that one as shear modulus. Okay? Shear modulus. What is shear modulus? Simply, I can say that it is the ratio of shear stress to shear strain. Now, modulus of rigidity or shear modulus is also represented as G or C, or sometimes it is also called as N. I don't get confused with all these things, right? You can follow either C, G, or N. Now, modulus of rigidity, as I'm showing it on the screen, it is the ratio of shear stress to shear strain. Shear stress is represented as tau and shear strain with phi. So shear stress and shear strain were explained in the last class. For your convenience, I have posted the PPT in course web as well as the slides in the course web, PDF as well as slides in the course web. And not only those things, handwritten notes was also shared, right? You can have a look at that one for any clarification. So you can also post some questions and doubts, right? So in the course web, you can directly post some questions. I'll be answering to them, right? It is compulsory for all the students. Next, Poisson's ratio. What exactly is this Poisson's ratio? So Poisson's ratio is nothing but it is the ratio of lateral strain to the longitudinal strain. So lateral strain to longitudinal strain. So lateral strain can also be calculated as mu multiplied by longitudinal strain, where mu is called as Poisson's ratio. So you can also make a note of this particular, right? Students, you can make a note of this. Mu is equal to lateral strain by longitudinal strain, or we can calculate the lateral strain, which is equal to mu multiplied by longitudinal strain. Longitudinal strain, what do you understand by the term longitudinal strain? For example, I'm considering a material which has got some diameter, right? When there is an axial pull along the direction of its axis, right? Axial pull itself is the force which is applied along the direction of its axis. Either it may be in the longitudinal direction, that means either tensile force or compressive force. When you are pulling it apart, then what will happen? Slightly it will increase its length, right? When you are just applying the force in the inward direction, then what will happen? It will try to reduce its shape. I mean to say it will reduce its length. Suppose when you are pulling it in the outward direction, what will happen to its diameter? Will it be constant or will it be decreasing? An open question to you. I'm considering a rod whose diameter is capital D. You are applying some tensile force on that one. Suppose I'm considering a 1 meter rod, apply some tensile load on that one. Its length has increased to 1.5 meter. Will its diameter capital D remain same, or will it increase or will it decrease?
It will decrease, sir.
Obviously, it will decrease, right? So there is some decrease in the diameter to the original diameter. What do you call that one as?
Strain.
Strain, which strain it is? Is it longitudinal strain or lateral strain? Lateral dimensions are decreasing here. So when lateral dimensions are decreasing, then you call that one as lateral strain, right? Lateral dimensions are decreasing, you call that one as lateral strain. Now, how to calculate lateral strain? We have Poisson's ratio here. When you multiply longitudinal, it is very easy to calculate the longitudinal strain, right?
Yes, sir.
How do you calculate longitudinal strain? We can calculate it by using Young's modulus as well as stress. Young's modulus, please remember, capital E is equal to stress divided by strain, sigma divided by E. Now, what will be small e? Strain is equal to sigma divided by capital E. Simple relation, right? So from that one, you can calculate the longitudinal strain. Now, when longitudinal strain is multiplied with Poisson's ratio mu, right, you will get lateral strain. See, whenever you see this type of thing and whenever I'm explaining something like this, right, you can make a note of these things, right? Thank you. Next slide. So we were also discussing about factor of safety in the last class, but just I have shown you what exactly is factor of safety. I did not explain it, right? What is factor of safety? Can anyone explain what exactly is factor of safety in simple words? In 1 minute. Make it fast. చెప్పండి ఎవరైనా
Work to be done without damaging the materials.
Okay, providing additional safety to the material. Can I call it as providing additional safety to the material so that it will not get damaged? Can I call that one as factor of safety? Anachandi?
Yes, sir.
Taking additional precautions to anything, whatever you are doing. Can I call that one as factor of safety?
Yes, sir.
Suppose you are writing the assignment, right? When you are writing the assignment, you have solved a problem. You took a scanned copy of that one. You have sent the assignment to my mail, right? And after sending the assignment to my mail, you have just checked it once or twice. You have checked it once or twice whether the assignment is sent or not. Can you call that one as factor of safety?
Yes, sir.
Yes. After writing the assignment or after writing your examination, it is a general practice of all the students to check the question numbers. Why do you check the question numbers? Whether you have written it correctly or not. Chepandi. Do you check the question numbers correctly or not? Whether you have written it correctly or not. Enduku check చేస్తారు? Why do you check it?
For safety purpose.
Yeah, for safety. I mean to say, suppose if you have written it wrong, then what will happen? You will lose some marks. What are you doing there? You are checking it once again, right? You're checking it once again, right? That is called as factor of safety, right? Okay, so those are in different what we say terminology. For example, you have written some examination, you are checking it once or twice, all the answers. That may be called as factor of safety. You are checking all the question numbers. That may be called as factor of safety. Suppose you are tying a knot, right? You are taking a thread and you are tying a knot. Suppose we have recently what we say a Hindu festival, right, which is Rakhi. Your sister might have tied you some Rakhi, isn't it? Right? Just only one knot is not enough. What she has done, she might have just tied 2 or 3 knots. And that is called factor of safety. Why factor of safety is needed over there? Rakhi katkunarandi. Me sister em chesaru, just she will be tying you 2 or 3 knots. Suppose okate mudi vesaru anukondi, then what will happen? After 1 or 2 hours, it will be gone, right? It will be released from your hand. So for factor of safety, she will be tying you 1 or 2 knots. That is called factor of safety. I have explained you factor of safety in simple, right? Okay. Now, coming back to the technical terminology, in engineering, factor of safety, which is also called as safety factor, right? We can also call that one as safety factor. It expresses how much stronger a system is than it needs to be for an intended load. Okay, for example, I told you in the last class that I'm considering a metal scale, 100 Newton load is applied on that one and it is bending in the downward direction, right? For 100 Newton load, it is bending in the downward direction. When you increase the load to 101 Newton, what will happen? Permanent deformation will occur. Now, in order to avoid permanent deformation, what I will do is I will provide additional layer over the surface. I'll provide two scales. I'll attach two scales. What are you doing there? You are strengthening the material, right? For safety factor, you are strengthening the material over there. Okay, so factor of safety usually refers to one of these two things. Just have written two things. You can just look at those things on the screen. The actual load bearing capacity of the structure. Actual load bearing capacity of structure. It depends on actual load bearing capacity of the structure. Or second one is the required margin of safety for a structure or component according to the code or law or design requirements. And for example, I have designed a scale and I'll say that this scale can bear only a load of 100 newtons. That means it's not possible for that particular material to bear more than 100 newton, right? For factor of safety or safety factor, what you will do is when you are loading the material, you will not load it more than 100 newton. And then suppose my father and your bike on each other. You got a new bike on your birthday, right? And on a bike, only two people can ride, a rider and a pillion, right? Now, most of the students, right, nowadays, you can see they are not following the safety factor. I mean to say, only two people can travel on a bike. Now, what they will do? They'll call one more student and make them sit either at the corner of the seat or in the middle, and they'll go triple riding. Is it safety? Is it safe for you? No, it's not, isn't it?
Yes, sir.
In a similar manner, you might have seen some public transportation, right? There are many public transportation facilities. For example, we have autos, right? On the auto, it will be clearly written as 4 in all. That means it can carry 3 people along with a driver. But do they actually carry 4 people in the auto? Respond. Can anyone?
No.
No, you might have seen nearly 10 people sitting in an auto, right? There are 3 people sitting beside the driver. Driver will be hanging from the window, and there are 5 people, right, who are sitting at the back, congested, right? There is no ventilation. It's very tight, and the auto will be leaning towards one side or the other side. Not only autos, right? You might have seen our TSRTC buses, right? TSRTC buses. So the maximum seating capacity only 60. According to the design requirement, the person who has designed the particular what we say bus, what he will do is he will say that only 60 people can sit in this bus and it is a maximum capacity. But the bus driver or the conductor, they will push more number of travelers or passengers. They will carry nearly 100 to 110 people in some critical situations, in rush situations. So is it safe for those type of things? It's not safe, isn't it? So already design requirements are given. For an auto, it is only 4. For a bus, it is only 60, right? But what we are doing, we are increasing the loading capacity on that one. It's not possible to increase it. Okay, now coming back to this factor of safety. Now, technically speaking, or mathematically, it is written as factor of safety is the ultimate stress to the permissible stress. The ratio of ultimate tensile stress or working stress to the permissible stress. Okay, ultimate stress to the permissible stress. We call that one as factor of safety. Okay, so I think factor of safety is very much clear to you, isn't it? Shall I go with the next topic?
So what is this ultimate stress?
Ultimate stress. So maximum load which is applied on any material, right? The stress which is produced to the maximum load which is produced or applied, right? That particular stress is called as ultimate stress. Suppose I told you within elastic limit, stress is proportional to strain, right? We know it from Hooke's law. So I told you one simple example. A scale can carry 100 newtons of load. That means after 100 newton, what is happening there? It is permanent deformation. There is some permanent deformation. That means up to 100 newton, stress is directly proportional to strain. Up to 100 newton, stress is directly proportional to strain. That means after 100 newton, what is happening here? There is some permanent deformation, right? So maximum load carrying capacity of that one is 100 newton only, or maximum resistance offered by that particular material is only 100 newton. So to a maximum resistance offered or maximum load applied, 100 newton divided by the surface area over which it is being applied, right? You can call that one as ultimate stress. Okay, so just a simple example here. In the future or in the next class, I'll be explaining you in stress strain diagram what exactly is this ultimate stress and permissible stress. Okay, see, reload actually. Stress strain diagram, right? I don't know how many of you have seen the notes. So when you're plotting stress against strain, right? Strain on x-axis and stress on y-axis, you call this thing as a stress strain diagram. Okay. Here on the graph, you can see there are some alphabets, right? Capital O, which is located exactly at the origin. And we have capital A. Next we have B. Next we have C. Next we have D and E, right? So I have also made a handwritten notes in which the stress strain diagram is clearly given, right? So there are some differences between the picture which I have shown here and here. D and E are slightly varying here, right? Point of failure, right, as well as point of failure over here are totally different. As you can see here, stress sigma in Newton per millimeter square is on the y-axis and strain E is on the x-axis. Now, from point O to capital A, right, the variation of stress and strain is linear. That means stress is directly proportional to strain in between O to A, right? Stress strain diagram is also when we conduct some experiment tensile test on a mild steel bar or a torch steel bar or any material, right? And we calculate the stresses and strains from the particular experiment. We can easily draw the graph. Okay, so ఒకవేళ మీకు laboratory experiment జరిగితే ఇది అర్థమయ్యేదండి, but in the next tomorrow we have laboratory session, right? I'll explain you what exactly is this tension test, right? In tension test you will be coming across this stress strain diagram. So it's very interesting experiment actually. Okay, see, from point O to A it is linearly varying. That means up to point A stress is directly proportional to strain. Linear and straight line. Stress is directly proportional to strain, right? So it is obeying Hooke's law up to point A. Now, exactly up to point A, whatever the stress which is developed, right? You call that one as proportionality limits, right? Limit of proportionality limit, or up to point A, it is a limit of proportionality. Okay, it will be following some what we say linear variation, and the stress will be directly proportional to strain. Now, what will happen after point A? You can just see it on the screen. After point A, it is not linear. Slightly, there is a small curve which is bending towards B, right? Okay. Now, what is happening in between A and B? What is happening in between A and B? See, the point B here, it is called as limit of elasticity or elastic limit. Okay, up to point A, it is linearly varying, but proportionality limit, it is called as proportionality limit. Point A is called as limit of proportionality, but limit of elasticity or elastic limits will be up to point B. That means it will be proportional. Stress will be directly proportional to strain. At point B, it is called as limit of elasticity or elastic limit. From point A to point B, slightly there will be a small curve. Okay. Now from point B to point C, right? There is a curve which is bending towards point C, right? So exactly at point C, you will find large extension, yielding point under. Yielding point under. Do you know what exactly is this point of yield or yielding point? Suppose I am just trying to expand a plastic wire. After some time, what will happen? It starts to yield, right? It will start to yield, right? Permanent deformation will start from there. Okay. Now, exactly from point C to point D, a perfect plasticity in the material you can find. Okay, it behaves as a plastic material. Plastic material, as if you are pulling a chewing gum. You know very well about chewing gum, isn't it? When you take a chewing gum and when with your fingers, when you pull it hard in the outward direction, what will happen? Behaves as a plastic material and it goes on expanding. It goes on expanding. Such type of material is called as plastic material. Any material in between C and D is perfectly plastic and it accelerates its strain. Accelerates its strain. Goes on expanding. Now, exactly at point C, it is called as point of sudden or large extension. You call that one as what actually? Yield point. You can call that one as yield point. Now, up to point D. Now, after point D, and after point D, there is no material which is left for increasing its length. Okay, strain is not possible after point D. But the graph, whatever the thing you see over here, up to point E, maximum loading, ultimate stress or ultimate strength is obtained exactly at point E. Okay, point E over here. After point D, there is no material which is left for expansion. That means strain tightening or strain hardening will take place exactly at point D. Is it clear to you? Right. Now, exactly.
Screen కనబడతలేదు సార్.
ఏం
Screen
కనబడతలేదు?
కనబడతలేదు సార్.
స్క్రీన్ కనబడతలేదా? మరి అప్పటి నుంచి ఏం చేస్తున్నారండి ఎక్స్ప్లెయిన్ చేస్తుంటే?
ఇప్పుడే సార్ జస్ట్
పోయిందా? Share it once again. స్క్రీన్ పోయినప్పుడు చెప్పాలి ఇమీడియట్ గా. ఓకే, is it visible to you now? Huh? No. What is the on the screen?
Blank screen, sir.
Blank screen. Right. Is it visible to you now?
నో సార్.
No sir.
How come it is possible? Wait, let me check. There are some technical difficulties. Okay, ఇలాంటివి వస్తూనే ఉంటాయండి. Don't worry about this thing. Just మీరు ఎక్కడి వరకు విన్నారండి? Just let me.
Point C and D, sir.
Point C and D.
Point
Okay, up
C.
to point C and D. Okay, no problem. No problem. No problem. Just wait. I'm just checking the network. Can you see? Hello. Who is available?
Sir, I can't hear your voice.
No, is not audible.
Hello?
Not clear, sir.
Yeah, wait a minute.
It's clear now.
Is it clear now?
Yes, sir.
No, sir.
Yes, students. Am I
Yes,
audible?
sir. Yes, sir.
Yes, sir.
Am I visible?
No, sir, you're not visible.
Sir. Yes, sir.
I have
Yes,
switched
sir.
on my camera actually. ఏ నెట్వర్క్ సక్క లేదండి అది డోంట్ వరీ అబౌట్ దిస్ బయట వెదర్ సరిగా లేదు కదా సో ఐఎమ్ యూజింగ్ ఏ పర్సనల్ హాట్స్పాట్ దట్స్ ఐ హావ్ కనెక్టెడ్ టు ఏ పర్సనల్ హాట్స్పాట్ దట్స్ వై దేర్ మే బి సమ్ టెక్నికల్ గ్లిచెస్ వినబడుతుందా ఇప్పుడు ఓకేనా
Yes, sir.
Yes, sir.
ఓకే
Yes,
జస్ట్
sir.
ఐఎమ్ షేరింగ్ ద ఎవరన్నా నాకు చెప్పండి స్క్రీన్ షేర్ చేస్తున్నాను
Okay,
అండ్ మీకు ఏం కనబడుతుంది స్క్రీన్ పైన చెప్పండి ఓకే రైట్ తరుణ్
sir. అది MS Teams కనబడుతుంది.
స్క్రీన్ కనబడుతుందా నేను పీపీటీ
Yes,
ఆన్
sir.
చేస్తాను ఇప్పుడు పీపీటీ ఈజ్ ఇట్ విజిబుల్ టు యు నో
Yes, sir.
రైట్ ఓకే రైట్ వెరీ గుడ్ ఇస్ ఇట్ ఓకే నౌ పీపీటీ
Yes, sir.
ఓకే బయట వెదర్ కొద్దిగా బాగాలేదండి అండ్ ఇంటర్నెట్ ఈజ్ ఆల్సో లిటిల్ బిట్ స్లో ఇట్ మే బి మై ఇంటర్నెట్ ఓకే డోంట్ వరీ అబౌట్ యువర్ ఇంటర్నెట్ సో ఐ హావ్ కనెక్టెడ్ టు మై పర్సనల్ హాట్స్పాట్ ఫ్రమ్ మొబైల్ దేర్ విల్ నాట్ బి ఎనీ టెక్నికల్ డిఫికల్టీ ఫ్రమ్ నౌ ఓకే obviously it will happen isn't it don't worry about this thing now after point D we call this thing as strain tightening or strain hardening right exactly up to point E it will take the maximum loading okay maximum loading will be taken up to point E now what will happen after point E can you tell me what will happen after point E cross sectional area will reduce and local extension will occur okay and exactly at point F sudden failure will occur okay
Yes,
is it okay for you
yes, sir.
Yes, sir.
okay the same points are given in the PPT I have explained you right here so plastic deformation permanent set and at point E failure will occur so this PPT will also be shared to you don't worry about this one okay coming back to the conclusion of this stress strain diagram an object is brittle if point D and E are very close okay see from I'm just giving you some conclusion inference so an object is brittle how to justify an object for example I'm considering 2 points D and E there are 2 points on the graph D and E if the points D and E are very close that means a sudden failure has occurred what does it mean actually it is a brittle material right for example I'm taking glass right a glass jar, it is a brittle material. Okay, if at all it is just dropped onto a floor, it will be broken into pieces. Okay, an object is said to be ductile if point D and E are very far. Ductile and for example, I'm taking a rubber band D and E. For example, we have point D and over here it is E, right? The distance between D and E are very far, right? Nearly, as you can see here, it is very far away from point D, right? Point E is very far away from point E. If 2 points D and E are very close, you can say that it is a brittle material. Right? If D and E are very far away from each other, then what can you predict from that one? The material is ductile in nature, right? Ductile in nature. It is taking a lot of tensile, what we say load. That means its tensile strength is very high. For example, you can take metals, gold, silver, etc. All these material, right? They provide some what we say good tensile strength, right? That's why the point D and E, when tested, right, will be far away from each other. Okay, see, elastic substances like rubber have large elastic region. Large elastic region. For example, we can take a spring or caterpillar. Caterpillar, you can see there is a picture which is given over here, right? Or tissue of your arteries. Artery. What is an artery? Okay, let's forget about this thing, right? There is a small tissue of your heart. It will be expanding and contracting. Okay, now this is regarding the stress strain diagram, and I have given you some conclusion how to justify a material based on the graph which is given or based on the graph which we have tested for a material, right? Okay, recapitulating here, up to point A, you can call that one as limit of proportionality, and exactly at point B, you call that one as limit of elasticity or elastic limit. Next, up to point C, you call that one as point of sudden or large extension. Point of large extension or yield point, you call that one as yield point, right? At point E, you call that one as point of maximum load or ultimate stress or ultimate strength. And what exactly is point F? Point F is called as failure. And after point F, there will not be any curve which is developed. Is that clear to you? Respond.
Yes, sir.
Right, very good.
Yes, sir.
Yeah, right, very good, very good. Okay, now students, in assignment number 1, I gave you a similar type of question, right? Now what you need to do is write down this question. We'll be solving the problem. I'll explain you how to solve the problem. Shall I dictate the question or is it visible to you on the screen?
It's visible.
Okay, I'll give 1 minute time. Make a note of this problem. We have 15 minutes to go, right? At least 1 or 2 problems I'll explain. I'll share the same thing again so that you can practice the problems. Addition to this one, assignments are also given and some extra problems are also given in your assignment. Okay. Now the first problem. Raskuntunara? Okay, I don't know whether how many of you are doing this thing or not. Immediately after completion of the class, take a snap, picture of your notebook, write this problem, whatever you have written in your notebook, take a picture of that one and post it in the group. Anyone who has not posted this problem in the group, right? I'll call you personally and I'll ask you what happened to you. Write down the problem. Problem solve చేసిన తర్వాత గ్రూప్ లో పోస్ట్ చేయాలి. I should see everyone writing the problem. Okay, I'm just saying it all out. A load of 5 kilonewton is to be raised by means of a steel wire. Find the minimum diameter of steel wire if the stress is not to exceed 100 megapascal. Okay, so I'll explain the problem to you first, then we'll go with the solution. There is a load. How much is the load? 5 kilonewton. That means it is 5,000 newtons. 5,000 newtons. Now that load need to be raised by means of a steel wire. There is a steel wire which is attached to that one, and by using the steel wire, we need to lift it. We need to lift it. So you might have seen cranes, isn't it? A crane which is lifting some load. In a similar manner, a 5 kilonewton, 5,000 Newton load need to be lifted up with the help of a steel wire. Now we need to determine what should be the minimum diameter of that steel wire if the stress in that steel wire should not exceed 100 megapascal. Now what will happen if the diameter of the wire is very little? The stresses in that material will be increasing or decreasing based on the diameter. Now here we have the data, given data. What is the given data? Load capital P, which is given as 5 kilonewton. Make a note of that one. Given data, load capital P is equal to 5 kilonewton or 5,000 Newton. Babu, Tarun Bandari,
Sir.
you post in your personal group,
Yes, sir.
right?
Yes,
That this problem need to be solved by all the students, and a picture of the same with your roll number should be posted in SOM group.
Okay,
I'll verify each and every student's picture, right, along with your roll number.
yes, sir.
Right. So from next class onwards, I'll be teaching it on a whiteboard. Okay. You can see me explaining the problems on the whiteboard live.
Yes, sir.
Okay. Given data, load P is equal to 5 kilonewton. How can we write 5 kilonewton as it is 5,000 Newton? And stress sigma is given as 100 megapascal, right? That means maximum stress, it should not exceed 100 megapascal. Okay. Now, I'm considering small d as the diameter of the steel wire. Let us call small d as the diameter of the steel wire. Now, how to solve the problem? See, I gave you the data which is required, the given data. Now, solving a problem is a beauty actually. Step-by-step solving is a technique, and it requires no great skills. No great skills are required. Just you need to identify the formula. Which formula need to be used? What is the outcome of this particular thing? Right? So step 1, identify the formula required. ఇలా రాసుకోవాలండి ప్రతి ఒక్కరు. ఈ ప్రాబ్లమ్ సాల్వ్ చేయడానికి నాకు కావాల్సిన ఫార్ములా ఏంటిది? ఇక్కడ ఏం అడిగాడు? We need to determine the minimum diameter. In order to determine the minimum diameter, diameter అనేది దేంట్లో ఉంటుందండి? From area formula we can calculate the diameter. Now that area formula can be used in one more formula that is called as stress. That is called as stress, right? Now here the required formulae are stress sigma, which is equal to load divided by area, or P by A. And from the same formula, cross-sectional area capital A is equal to pi by 4 multiplied by diameter square. Pi by 4 multiplied by diameter square. Okay, this is the required formula from which we know the area. A is equal to pi by 4 multiplied by d square. So we cannot calculate area because diameter is unknown to us. But load is given to us and stress is also given to us, isn't it? How much is the load? 5,000 Newton. P is equal to 5,000 Newton. And stress sigma is equal to 100 megapascal. 100 megapascal. 100 Newton per millimeter square. 100 Newton per millimeter square. Okay. Now coming back to the next step. Given P is equal to 5,000 Newton. Now coming to the second step, additional formulae which are required. Already we know that one, cross-sectional area A is equal to pi by 4 multiplied by d square. And stress is given to us, sigma is equal to 100 MPa, 100 Newton per millimeter square. Now coming back to the third step, substitution. Sigma is equal to P by A. A is pi by 4 multiplied by d square. Just substituting all the values. Sigma is 100, P is 5,000. In the area, diameter is unknown to us, which need to be calculated. Now I have substituted all the values and calculated the diameter, which is 7.98 millimeters. Or you can also take that one as 8 millimeter. So to carry a load of 5,000 Newton with the help of a steel wire, or steel rod, the diameter, minimum diameter required is 8 millimeter. 8 millimeter. Now, an open question to you all. What exactly will happen when the diameter of that steel wire is less than 8 millimeter? చెప్పండి ఎవరన్నా 8 millimeter కంటే తక్కువగా ఉంటే ఏమవుతుంది?
Permanent deform, sir. It will permanent deform, sir.
Yeah, okay. The wire will permanently deform, right? Or it may fail after some time. Like chewing gum, it will be expanding. And after some time, what will happen? It will break, right? Not possible to carry 5,000 Newton with a wire whose diameter is less than 8 millimeter. Right. Is it clear to you, all the students?
Yes, sir.
Shall I go with the next solution, next problem?
Yes, sir.
Yes, sir.
Right. Okay. Next question. I don't know the next question. A rod 200 centimeter long and 1.6 centimeter diameter. A rod 200 centimeter long and 1.6 centimeter in diameter is subjected to an axial pull. Is subjected to an axial pull. Axial pull under tensile loading. Is subjected to an axial pull of 40 kilonewton. Is subjected to an axial pull of 40 kilonewton. If the modulus of elasticity, that means Young's modulus, of the material is 2 into 10 to the power 5 megapascal. MPa is written wrong over there. M capital P and small a. Okay, you make it corrected in your notebook. If modulus of elasticity of the material is 2 into 10 to the power 5 megapascals, that means 2 into 10 to the power 5 Newton per millimeter square. Determine. First one is stress. We need to determine the stress in the material. Second one is strain in the material. Third one is elongation of the rod. Stress, strain, and elongation of the rod. Right? Is the question clear to you?
Yes, sir.
Right. Okay. That's well and good. Now, shall I go with the solution?
Yes, sir.
Yes, sir.
Right. Okay. Now, see, just looking at the problem and looking at the data, can you tell me how to solve the problem? How to calculate stress, how to calculate strain, and how to calculate elongation? Load is given to us. Length of the rod is given to us. Diameter of the rod is given to us. Can somebody recapitulate what exactly is the diameter of the rod and length of the rod? I'll call the roll number. Roll number 98. Who is roll number 98? Do you have roll number 98 in your class?
Yes, sir.
Yes, ever roll number 98?
Present, sir.
Yes, roll number 98. Cheppu, etla solve cheyala problem? Given data cheppu bayatiki. What is the given data?
Given data, length of rod is equal to 200 centimeters ఇచ్చింది సార్. దాన్ని millimeters లో మార్చుకోవాలి సార్ 2000. తర్వాత
Right, very good.
డయామీటర్ ఇచ్చింది సార్. అది రాడ్ సార్. దాన్ని millimeter లో మార్చుకున్నారు సార్.
Yes, very good.
ఫోర్స్ కూడా ఇచ్చింది సార్ 40 కిలోన్యూటన్స్ లో. మన న్యూటన్స్.
Right. Okay, very good. Rule number 85.
Sir.
Rule number 85. Etla solve cheyala. Stress etla calculate chesaru repu. What is stress?
Stress is load by area.
Load is given. Load is given. How much is load?
40,000 newtons.
Right. Do you have area here?
We converted to formula.
Right. What is the formula to calculate area when diameter is given to you?
pi by 4 into d square.
Right, very good. Pi by 4 multiplied by d square. Next, strain. Strain ఎలా calculate చేయాలండి? సింధు రెడ్డి చెప్పమ్మా. బండారి సింధు రెడ్డి, CR.
Yes, sir.
Definition of strain. What is definition of strain?
A ratio of change in length to the original length.
Right. Do we have change in length? Delta L ఉందా అక్కడ మనకి?
No, sir.
Original length ఉందా?
Yes, sir.
But okay. What is Young's modulus?
Stress by strain.
Okay. Sigma divided by E. E is equal to capital E.
Yes, sir.
Now if we interchange small e and capital E from the
Sir?
formula, what will happen? Can I write strain small e is equal to stress divided by Young's modulus?
Yes, sir.
Okay. Now from that one, can I calculate strain?
Yes, sir.
Strain small e is equal to stress. First దాంట్లో
Stress
stress
by
calculated.
Young's
Right. Stress divided by Young's modulus. That means we have to calculate stress first.
Yes.
Young's modulus is known to us 2 into 10 to the power 5. Now stress divided by 2 into 10 to the power 5 will give us what?
Stress. Strain.
Strain. Right. Now when strain is known to us, elongation, can we calculate elongation? 93. Who is 93?
Sir.
Strain formula చెప్పండి.
Strain stress by Young's modulus.
Strain, general formula for strain, delta L by L, change in length by
Original length.
change in length అంటే delta L divided by capital L. Right. Strain calculate చేసాం already. Can we calculate elongation? Third one, delta L is equal to strain multiplied by original length. Right. Okay. Now students, very good. You are giving a very good response. All the students are very, what we say, concentrated, and you are giving very good response. I appreciate each and every student. Right. Okay. Step 1, identify the formula needed. Now, how many formulae do you see on the screen, Tarun Bandari?
Sir,
How many formulae do you see on the screen?
4 formulas. Sir.
Right. The first formula is stress
Stress.
sigma, which is equal to axial pull divided by cross-sectional area. We can calculate cross-sectional area. A is equal to pi by 4 into d square. That is, I have already calculated the area. That is equal to 201.06 millimeter square. The diameter is given to us. Right. D is equal to 1.6 centimeter. That is 16 millimeter. Now area I have calculated pi by 4 into 16 millimeter square. That is 201.06 millimeter square. Next formula required is Young's modulus. Young's modulus E is equal to tensile stress by tensile strength. That is sigma divided by E. The next formula which is required is strain. All E is equal to delta L by L. Now this formula can also be written as E is equal to sigma by E. Stress divided by Young's modulus. Okay. Next, step number 2. From the required formula, identified formula and the data which is given to us, I am substituting. Step number 2. Stress is equal to load divided by area. Load is given to us 40,000 Newton and cross-sectional area is 201.06. What are units of P here? P, load.
Newton. Is on Newton.
Newton.
I have converted that one to Newton. Okay, student, P is in Newton. What are units of area?
40,000
Meter square.
Millimeter square.
Millimeter
Right?
square.
Now it will become 40,000 Newton divided by 201.06 millimeter square. Newton per millimeter square. What is Newton per millimeter square?
Megapascal.
Right, very good. It is called as megapascal. Okay, now 40,000 divided by 201.06, it is called as 198.94 megapascal. We got one answer. Next one, strain. E is equal to sigma divided by E. Already we have calculated stress. That is 198.94 divided by E is 2 into 10 to the power 5. That means I have written that one as 2 lakh. 2 lakh, right? 198.94 divided by 2 lakh, that is equal to 0.00099. Do we have units for strain? 96. Who is 96?
Sir, present, sir.
Strain ki units enti?
Sir, strain, sir.
Yes. No units.
There, sir, newtons.
Ledu. Strain undadandi. Strain. Okay. No units for this. Next, see, from this one I can calculate elongation. So, see, from the formula, strain is equal to delta L by L. Strain is delta L by L. Now, delta L will be equal to small e multiplied by L. So, already we have calculated small e, that is equal to 0.00099. Right? Multiplied by total length. What is total length? 2000 millimeter. Now 2000 multiplied by 0.00099, that is equal to 1.98 millimeter. And 40,000 Newton load apply chesinappudu, it is giving a total extension of 1.98, approximately 2 millimeter. So these are the answers which I have obtained. Stress sigma is equal to 198.94 megapascal. Strain E is equal to 0.00099. Elongation delta L is equal to 1.98 millimeter. Right. Is that clear to you now?
Yes, sir.
Students?
Yes, sir.
Right. Do you have any doubt regarding this problem? No. In the next problem, in the next class, I am going to explain few more problems. Okay. Problem number 3 will be explained in the next class. Right. Now, recapitulating once again whatever I have explained. We have learnt about Hooke's law. Next, modulus of elasticity or Young's modulus. Values of different values of E for different material. Next, modulus of rigidity or shear modulus. Poisson's ratio. I have also explained you what is shear strain and longitudinal strain. It was explained in the first class. Next, I have explained you factor of safety, which is ultimate stress by permissible stress. I have explained you about stress strain diagram and what are the different proportionality limits. Key features. These are key features of the elastic, what we say, curve or stress strain diagram. And I gave you conclusion and how to identify the material based on the stress strain diagram. And we have solved 2 problems in today's class. Right? Okay, I'm stopping the sharing now. There are 51 students today. I'm taking the attendance, download attendance list. Just wait for 2 minutes. Don't leave the class now. Yes, somebody recapitulate whatever I have explained today. In 2 minutes, I'm going to end the session. Anybody? Recapitulate. Tarun.
So today we learned about Young's modulus and lateral strain and longitudinal strain.
Poisson's ratio.
And factor of
Poisson's ratio, factor of safety, and
safety.
curve between stress and strain, and how to identify a material based on this curve.
Right. Very good, very good. Inka.
And we solve the problems based on stress strain.
Okay, very good, very good. ఇంకా ఓకే, ఈ రోజు ప్రజెంట్ ఉన్న వాళ్ళనే నేను ఒకసారి చెప్తున్నాను, ఇక్కడ చూడండి. రూల్ నెంబర్ 67 present, 78 114 77 63 92 98 85 108 79 119 62 97 81 80 65. Next 80 111 103 74 69 95 102 96 107 75 70 113 104 87 64 93 76 71 68 73 86 118 90 83 105 110 61 84 94 112 82 109 100 116 72 89 66 120.
Sir,
Okay.
100%, sir.
Yeah, 100%. ఇప్పుడే చెప్పాను.
Sir, 112 also.
Sir, 94 also.